A warm welcome to all of you here from Germany, from Maschinenfabrik Rheinhausen, for this roundtable discussion on phase-shifting transformers. The changing world in the energy sector, the renewables, is on one side a blessing. On the other side, it creates, let's say, a challenge for the network system, for the grid system. The transmission system was planned in the 1900s. It was a unidirectional power flow. There was the generation, there is the transmission, distribution, and the consumption. This somehow changed now with the new forms of generation, with wind farms, with solar, the variable power generation, the variable directions of loads, of power, the different impedances of lines, all these, it changes from a steady power flow into a floating bi-directional power flow. Transmission utilities have actually less direct influence in order to control these changed conditions. Possibility with phase-shifting transformers control this power flow and to control unwanted power flow, to enforce certain directions of power flow, to block power flow, or even to reverse power flow. And Germany actually has a lot of experience in these phase-shifting transformers. And it's not only in Germany, it's phase-shifting transformers over the entire Europe. We will answer a question, or maybe there are questions, why do we have in Germany and Europe so many phase shifters? What are the regulating aspects? What are financial implications?
Okay, one major driver for these phase-shifting transformers is the changed situation in the grid. And this is possibly due to the installation of renewable sources. So here in this introductory slide, you can see how the renewable energy has developed in Germany. We set the Renewable Energy Act into force in early 2000, and you can see by the end of 2000 already a lot of wind energy was installed in the northern part of Germany, close to the North Sea border, which is the best position for wind energy in Germany. You don't see any PV systems right now, but a couple of years later, in 2006, you can see that already the first PV systems have been installed. And similar to the wind energy, these PV systems have been installed at the best locations, which is the south part of Germany. The wind is going to the second best positions already, so we are moving south with the wind and we are moving north with PV systems. And in 2016, Germany looks like this, quite colorful, as you can see. Although the numbers are from 2016, the development of renewable sources lost a little bit of dynamic in 2012. So this is quite actual. These numbers have a little increased in the last couple of years, but the dynamic has been lost a little bit. Still, we are going to meet the requirements that our government has set. So there's more than 55,000 megawatt of wind and 55,000 megawatt of PV systems in Germany right now, and the installation is still going on. If you want to build a wind turbine, for example, in Germany, you cannot choose the best position anymore, as you can see in this map. So you have to go to the position that is still open. And this position is mostly in the eastern part of Germany. Unfortunately, there's not very much load. This load is in the south and in the west. So by building new renewable sources, we cause a regional imbalance between production and consumption. And this causes congestions in the system and also loop flows and transits. This is what Mr. Panzer said, as unwanted and unscheduled flows. And we have to be able to mitigate these flows, to remedy congestions and so on. And therefore, phase-shifting transformers are one very nice possibility. This is the regulatory framework that you can see here. I think it is very high level in this slide. It's probably very similar in India too. So we have to follow a three-step escalation plan. First, if there is a problem, we have to try non-costly measures. We're talking about congestions here. So we have to try topological measures first, which means switching on or off lines, tapping transformers, and so on. To try to mitigate this problem. If this is not sufficient, we can move into the market. This is the yellow boxes here. So these are costly measures. The network operators have to spend some money to ask for help by power plants or by big consumers. And if this is still not sufficient, then the grid is endangered. Then we are in the red box. There is emergency plans have to be applied. So this is curtailment of renewable sources, for example, curtailment of conventional power, and probably curtailment of loads as well. So our phase-shifting transformer would be located in the green box. So this is a topological measure, which means it's non-costly for the grid operator, and therefore it has to be used in a very early stage of the congestion. In Germany, we have two main paths for congestions. One is north to south, and one is west to east. And here you can see the north to south main flow as the blue arrow. All of these lines are therefore utilized from north to south direction. Let's imagine the line in the central part of this picture is overloaded. Then we want to remedy this congestion using a PST, which means we will install a PST in a line to this line. So a series PST. And this PST can be controlled in such a way that it causes a circular flow that is in the opposite direction on this line. And as I said, it's a circular flow. The circle has to close somehow, and this is done using the parallel lines to this line that I want to remedy. So this means using this PST here means that the adjacent lines, so the parallel lines, will be burdened a little bit more. So this is very important. We have to keep this in consideration. So the flow is shifted from our main line that we want to remedy to parallel lines, which means that this PST does not affect only the specific line, but all lines in the system. And if you want to place several PSTs, this is very important, so the PSTs don't start to fight against each other. One solution to these loop flows are, for example, these PSTs. So we positioned them at the borders of bidding zones, which are the same as the borders, mostly the same as the borders of control zones in countries. So this is why it looks like that. From a technical point of view, this is probably not the best position for these PSTs, but it's a political compromise, so it works. Let's say there are 3 zones, A, B, and C, and let's imagine we have some power flow in this grid. And you can see in zone A there is some exhaust energy that is exported to the other zones B and C. and this will cause this base flow that is painted here in yellow. Now you can see zone A is exporting, and let's say the interconnector on top is the weakest one. So this is the one that gets congested first. And we want to remedy this congestion using a PST. So we will definitely place a PST here because it's the most effective position. And I showed you already that this PST will cause flows on all the other lines. So this is what the result may be looking. And you can see that our line where the PST is positioned can be very nice remedied. The congestion is gone, but you can see all of the other interconnectors are utilized a little bit more by the circular flow. So probably the second interconnector between A and B may be congested now. So yeah, why not place a second PST over here? This is the European thinking. And again, you see the result of this PST. And now if you have a look at the PST, the red PST, you see that the blue arrow and the red arrow are in opposite direction. So this is what I meant before these PSTs start to fight against each other. And this is an indicator that placing these PSTs at country borders is probably not the best idea from a technical perspective, because these PST now cannot use their full potential. They only, on the interconnector between A and C zone, you can see that these PSTs evoke a flow in the same direction, but placing another PST there is, again, probably not the best idea, because we can see the same effect now on the other interconnectors, that the arrows are in opposite direction. I can solve this solution with two PST, one between the zones B and C to shift the flows between north and south, and one PST on the weakest interconnector to shift between the weak and the strong one. So this would be a very nice, very cheap technical solution that works fine. But the problem here is the different regulatory frameworks in the European countries that prevent doing this situation. Maybe the regulatory framework in India is a little bit better, that you can probably do a technically more optimized solution than we did in Europe. I now want to show you some results from the interconnector between the German substation Röhrsdorf in Sachsen and the substation Radek in Czech Republic. And here in the picture you can see how this is set up. This is a picture from the substation Röhrsdorf. We have two PSTs over there, one from ABB and one from Siemens. And on the left side, you can see the plan. So the substation Röhrsdorf is a triple busbar substation. You can see the bus bars on top on the left picture. I skipped all of the inner German lines. We have these two PSTs over there. And what is a little bit special is these two bypass bus bars that you can see on the bottom. So we can short circuit these PSTs if we don't actually need them. This is a little bit has a little bit positive effect on the grid losses. So PSTs have been installed in the ENSO-E grid almost 20 years ago, the first PSTs. So there's a lot of experience in the ENSO-E region to plan and to operate phase shifting transformers. So we consider this state of the art, and that is why the German TSOs decided to place PSTs on these borders, especially on the eastern border of Germany. You can see in this case we used a PST type that has been installed a couple of times before. It's a so-called Diele type. It's a two-vessel construction that is used here, and it has a rated power of 1,200 MVA with 20% overload capacity. We have 65 taps, 23 in each direction, and these transformers each can produce a phase difference from 10 to 20 degrees. And we decided to place one of these PSTs on each line on the German part of the border, and the second PST on the Czech side of the border. So on this line, on this interconnector between Czech Republic and Germany, there are two PSTs in line. So it's a two-system interconnector, which means we have 4 PSTs installed on this interconnector. So in sum, on each line, we can have a maximum phase angle of 40 degrees that can be installed. This is a strong wind and low load scenario, which is considered to be sort of the worst case considering congestions and loop flows. And you can see that using this PST has a significant effect on all of the flows. So depending on the tap position, you can see in the left picture, we are blocking the flow. So from the voltage point of view, everything is fine. We redistribute the flow to all of the other interconnectors. In the middle, there is the neutral position. Now you can see that more than 1 gigawatt of flow could be blocked. And on the right-hand side, you can see the pushing position. So we are forcing flows through this interconnector to release flows on the other interconnectors, especially to Poland. And here you can see that we run into low voltages here. So the reactive power is, or the PST consumes a lot of reactive power, which means that this is necessary to compensate locally. Okay, so this is almost the end of my presentation. Let's summarize the most important parts. So I hope I could show you that PSTs are state-of-the-art in the European energy system, and that we have a lot of positive experience with these PSTs. They can really help remedy congestions in the system. And depending on our regulatory framework, we have to use them at an early stage. And the European TSOs are still planning to build new PSTs in the system. So in Germany, there are 3 more substations where the installation of PSTs are planned within the next 10 years. So the German TSOs think that PSTs are a great opportunity to deal with congestions and loop flows and unwanted flows. So I hope also that I could show you that placement and position strategies for these PSTs have to be planned in detail to maximize the output of this PST. We don't want to make these PSTs fight against each other. So planning and operation strategies need to be optimized best in combination with each other. So if you install PSTs in your grid, this can really help you if you do it properly. And one last word from my side, it's very important that you keep reactive power in mind and plan for compensation because these PSTs really need a lot of reactive power.
So first of all, when we start thinking about phase shifting transformers, then we would, of course, look at rated power, and this is not different to any other transformer, of course. But The next thing would be the phase angle. So we are not talking about percentage of regulation range. Now here we're talking about an angle in degree and how many steps we would need to realize a certain angle. So this would be different to normal transformers. Then, of course, rated voltage of the system line is important for the design. And in many cases, phase-shifting transformers are very huge pieces of equipment, and they have to be shipped around the world. And the shipping limitations, especially if you leave the waterway and you go on railway or on the road, can cause certain problems. So this is something that has to be considered, of course. And the OLTC performance requirements are a point for phase-shifting transformers. In many cases for OEMs that are new in this business, this is kind of a new situation because when you create a normal transformer, you would come up with a design, you select an OLTC and everything is fine and you go with it. This is different with phase-shifting transformers. If we look at phase-shifting transformers, a limited component in many cases can be the on-load tap changer. And if this is the case, you have to start with the ability of the on-load tap changer and then adapt your transformer design to be able to get out most of what you need from your phase-shifting transformer. So it can happen that you have to change your design based on the on-load tap changer. And another important thing is the short circuit capacity of the connected system. And if we look at certain designs, especially if we look at single core designs, we will see that later on, the on-load tap changer, if it's moved to the K position, how we call it at MR, you have no reactance, you have no impedance in your power line anymore. So if you have certain limits for short circuits, it can be the case that you need an additional reactor because in the K position, the single core design, you don't have any impedance that would limit your short circuit. And on the right-hand side, you see a table as an example with certain inputs we need to come up with the proper OLTC. People talk about overloads, yes, of course, but at the end of the day, it's not always clear what it's meant by the overload. And if we look at the standard, there are certain overloads. There's the normal cycling loading, and that's well defined by the standard. There's the short-time emergency load and the long-time emergency load. And sometimes we have customers that are coming up with seasonal loads, and this is all fine. But at the end of the day, we have to be very clear on that. Because one thing is we need the rated parameters and then we get the voltage across the tap winding and then we can charge the insulation for the OLTC. But what is special about this application, if we increase the load on a phase shifting transformer, the step voltage will increase as well. And this is very unique because if you look at a normal power transformer, if you increase the load, the step voltage is going to stay constant. But this is different here. So if you increase the step voltage with the load, the switching capacity of your on-load tap changer is affected. And this is something you have to consider. And this will lead to certain limits. What we see quite often is that phase-shifting transformers are operated in parallel. So if you operate a phase-shifting transformer in parallel, you have to be aware about the fact that the on-load tap changer is not always operated in a synchronous way of both units. That's just not possible. There always will be a time delay. So if you have different voltages on your booster windings, then you will create a circulating current between the phase-shifting transformers. And this circulating current will add up to the load current on your phase shifter. And for thermal reasons, that might not be the big issue maybe for a certain time, but the on-load tap changer must be able to handle this current. So in many cases, we would ask our customer, is there any parallel operation planned? And if so, what are the circulating currents? Because we have to consider them. If we look at single core designs, the potential connection of the tap winding, and there's one special design with a single core design where you get very high recovery voltages on the pre-selector, and in some cases they are so high that you cannot handle them with a tie-in measurement, and then you need shieldings on your windings maybe. So if you look at the regulation windings at the sketch in the middle, it can happen that you have to shield them because we just cannot handle the potential parameters there. And this is something that should be considered up front and not at the end of the design stage. And if we talk about interlocking, there are three different scenarios. So the first scenario would be interlocking between switching components inside the transformer. If you have, as we see it on the left-hand side, a two-core design with a booster application, and now you see at the booster we have an advanced retard switch. And in the exciter unit, we have a coarse fine winding arrangement. Then you only can operate the advanced retard switch if you put the terminals of the booster to the ground connection with the onload type changer in the exciter unit. So that means in this case, you have to bypass all the regulation winding in the exciter with the onload tap changer. That means you go to the end of the regulation, to the minimum turn position of the fine winding and to the minus position of the coarse winding. And then you have ground connection put to the terminals of the booster transformer. And in this, and only in this position, you are allowed to operate the advanced retard switch. So this interlocking will be realized by MR. So this is not the problem because we are focusing on that. So if we know the design, if we know you use advanced retard switch, we are going to realize this interlocking. But it becomes more difficult and more critical if we talk about interlocking between transformer and other components in the switchyard. And as we can see here on the sketch in the middle, that there is a bypass of these two transformers. And if you operate the bypass and the phase shifting transformer is not put to a neutral position, you basically have a voltage source that is short circuit by the bypass, and then you drive several kiloamps through this circuit, and this might not be good for your phase shifting transformer. So for that reason, it might make sense to have interlocking there. And the third interlocking condition is between transformers. As I already mentioned, if you have parallel operation of transformers, you might need an interlocking between these two units, that this difference in steps are not getting too huge, that you don't generate too big circulating currents. This is to consider, especially for OEMs here. If we look at the right selection of the OLTC, there are certain parameters that play a role. One thing is the PST design that determines the onload tap changer and especially its position. So if we look at the design or at the sketch on the left-hand side, you see a single core design. If we have a single core design, the onload tap changer is placed at the line end. So we have full voltage on the onload tap changer, and that would be a limit, of course, for the onload tap changer. We usually see that up to 245 kV. That would be a certain, certain limit. Above that, this design is not possible anymore. And another critical thing is, as I already mentioned, you have to look at the short circuit and your needs there in the grid, because if you go to the K position with this design, you don't have any impedance in the grid anymore. So there's nothing that would limit a short circuit here. If you look at the design at the right-hand side, it's a two-core design. And the onload tap changer here is sitting in the star connection, and you have the possibility with the different ratios of booster and exciter to come up with ratios that would allow you the optimal selection of an onload tap changer. And all other things are printed here that are important, as the step voltage, the max through current, of course. The phase shift has an impact as well on the step voltage. And insulation, of course, is critical for the OLTC here. If you look at point 1, that might be our working point for the onload tap changer. So that would be with nominal current. And now you would think everything is fine. And usually if you look at the standard would tell you that the switching capacity of your onload tap changer must fulfill the need that you can increase the load current twice of the nominal current, and then you're still within the red dotted line. So that would be the limit our OLTC is able to handle. Now you have to know with a phase shifting transformer, if you increase the load, the step voltage would increase as well. And in some cases, you have a working point where you would leave that red line. So if we double the load current from point 1, you would leave the red line to the right. So you would leave the switching capacity limit of our OLTC. So now my challenge would be to find the right maximum switching capacity to select a proper onload tap changer. And if I go to point 2, you can see this is not quite the double of nominal current, it's less than that. And I have now to choose a proper transition resistor, and that might be point 3, but at point 3 I don't have a transition resistor, so I have to use transition resistor at point 4 for this working point 1 we see here. And additionally to that, I have to reduce the maximum overload maybe to 1.5, for example. And if you go to the standard, the 6214 part 2, the application guide of onload tap changers, you will see there is a graph that will explain that this is accordingly to the standard, to the norm, because of the fact that the step voltage is increasing with overloads here. So that's very important. And the main message here is when you want to implement an onload tap changer to your transformer, and you would like to do that in a proper way, we need very close teamwork together with the OEM.